In this section of chapter 6, I'd like to go over Bohr's theory and matter waves. Now what you're looking at on the left hand side is neon light. So there is a particular color that's coming out of neon gas. Now this is something interesting because different elements give off different radiations. So we don't get continuous radiation. Continuous radiation means all the colors of light, like red, orange, yellow. I mentioned about this Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. That's all radiations of visible light. But interesting thing is most elements would give only some of these radiations rather than all. And that was something that scientists were trying to explain. Again, here looking at these spectra from certain elements, and these are called line spectrum rather than continuous spectrum that gives all the colors of light. And again, scientists wanted to explain the discrete wavelengths observed in the experiment. So what is causing these discrete lines rather than continuous line? Now Niels Bohr is the one first explained this. So he explained that by considering electrons in an atom remain only in certain orbits, just like planets around the sun. You know that there are different planets at different distances from the sun. Similarly, he assumed that electrons are in specific orbits and at certain distances from the nucleus. Now, when there is electron transition between these levels, then there'd be absorption or emission of radiation. Like when electrons go from lower level to a higher level, then there is an absorption of energy. If it drops from higher level to a lower level, then there'd be an emission of radiation or light or emission of energy. Now this is the expression that he came up with. Delta E, or change in energy, is given by HCRH. RH is called Rydberg's constant, 1.097 times 10 to the power 7 per meter. Inverse of NF squared minus inverse of NI squared. NF is the final state and NI is the initial state. We're talking about electron transition from one state to the other. Like if you follow the red line on the left hand side figure, that means that particular electron started at n equals to 1, at the very bottom level, and then it moved to n equals to 2. So the final n value is 2 in this particular case, and initial value is 1. So similarly, electron can even go to n equals to 3, 4, 5. Now, in those upper levels, they are not very stable. They usually like to come back to their original location. So when they do that, when they drop down, then it gives off radiation. That's shown with next arrow next to the red. And so keep that in mind. So whenever electron comes down from a higher level to lower level, energy is released. Bohr's model explains line spectrum. That means why elements, when they give off radiation, they don't give all those radiation wavelengths or all those colors. The answer is, if you go by the Bohr's model, you have a central nucleus surrounded by all orbits, and you don't have orbits at every energy. To explain it further, let's assume that level 2 has energy 6. Again, these are some of the numbers that I came up with so that I can better explain. And let's assume that level 3 has 10 unit of energy. That means whenever you have an electron in level 2, that electron must have that 6 unit of energy. If you have an electron in level 3, that must have 10 unit of energy. Now what is going to happen if electron moves from level 2 to level 3? So that means level 2, when it is in level 2, it would have 6 unit of energy. When it goes to level 3, it would have 10 unit of energy. So what happened to the difference? It must be absorbed, because you must have that extra energy to move from level 2 to level 3, and that energy is 4 unit of energy. And in this particular case, electron has to absorb 4 unit of energy before it moves from level 2 to level 3. What would happen if electron jumps back from third level to the second level? If it begins with third level, that means it has 10 unit of energy. When it goes down to 6 or second level, it would lower into 6. So having 10 to begin with, and at the end you have 6, what happened to the difference? Think it this way. You went to the mall with $10 in the pocket, and when you came back you had $6 in the pocket. So what happened to the difference? You probably went to a candy store and gave that $4 to somebody who is working at that store, and so in other words you gave away and gave $4, the difference. In this case, when electron jumps from higher level to lower level, the energy, excess energy, is given off. The difference in energy is given off. This is an interesting finding, and this was discovered by Louis de Broglie. His question was, if light can have both wave property and particle property. Now, in case you forgot, let me explain that to you. Light diffraction, because light spreads out through a tiny hole, that can be explained only by wave property. Wave property means light is like this, like any wave, like C wave, except that these wavelengths are very small. You can't even see it. Now, Einstein explained photoelectric effect by considering light as particles. Without considering particle nature, you can't explain photoelectric effect. Remember photoelectric effect? You have a metal plate and light is shining on the metal, electron is going out. And that can only be explained when light is considered as particle, because particle then transfers energy to electron, and then electron gets that energy, and when it exceeds the binding energy, then it would be getting out of the surface of the metal, and it would have kinetic energy. So we know that there are two properties of radiation or light. One is wave property, the other one is the particle property. I'm just writing down particle like this. So de Broglie then questioned, if light can have wave property as well as particle property, then the particles that we know, why can't they have wave property? So it was quite interesting, and later on they did some experiments with electron, and they found out that electrons do have wave property because it can diffract through tiny hole just like light wave does. So, and then he gave this expression, wavelength of an electron. Obviously now it is true for any matter, anything moving. So even you'd have a wavelength when you're jogging or running, and that wavelength would be given by h over mv. If you plug in all these numbers, you'd find that wavelength is so small. In your case, if you have your own mass known, and I'm sure you know your weight or mass, and if you plug in your velocity, you'd find that the wavelength is so small we cannot even see the difference. And it seems to us an object is moving in a continuous manner rather than in a wavy manner like this. But scientists can see it for electrons because electron is one of the smallest matter that we can think of. Now again, we're showing you the de Broglie expression, but before we do any problem, make sure that we stick to the units, right units. H, again, this is a constant called Planck's constant, 6.63 times 10 to the negative 34 joule times second. And joule is made up of kilogram meter squared per second square. So these are the units that go with joule. Since you're going to use that constant in this expression, h over mv, so your mass unit has to be in kilogram, consistent with the unit that you have in joule. Velocity will have to be meter and second, again because h has both kilogram and meter, so velocity must have meter unit per second. Now, next thing that I would like to tell you is every moving object has a wavelength. And with this in mind, let's go over homework problem from page 243. Let's do number 43A. The question is, determine the wavelength of 85 kilogram of person. So mass is 85 kilogram. So mass is 85 kilogram is skiing at 50 kilometer per hour. So velocity is 50 kilometer per hour. And since we need to calculate wavelength, the de Broglie expression is given by lambda equals to h over mv. And remember, the h value is 6.63 times 10 to the negative 34. So h is 6.63 times 10 to the negative 34 joule times second. And joule is made up of following units: kilogram, meter square per second square, and that's joule. And then you have the second here. So basically you'd have kilogram meter squared per second when you have joule times second. So keep that in mind. So we're going to use that unit when we do the calculation. So mass has to be in kilogram, and it is given in kilogram. But velocity has to be in meter per second, and we don't have meter per second. So let's now convert kilogram per hour to meter per second. So let's begin with that. So I'm going to write down 50 kilometer per hour. Now, in order to get meter and cancel out kilometer, I must have kilometer at the bottom. So kilometer at the bottom and meter on the top. And we know that kilo means 1,000. So 1 kilometer means 1,000 meter. You should read it like this: 1,000 meter or kilometer. So that checks with the bottom. Often, students mistakenly write down 1,000 or 10 cubed at the bottom. So that's not going to read right, because then it would be 1 meter equals to 1,000 kilometer. It's truly just the opposite way. 1 kilometer, kilo, always remember it's 1,000. It's 1,000 meter. So that's how it should read. Okay, now you can cancel out kilometer and kilometer. Let me show you with a different color. Kilometer, kilometer cancel out. And that would give you meter per hour. But I need to go get meter per second. Since hour is on the top, on the bottom, I need to have hour on the top so that they cancel out. So hour on the top, and I need to get second. Okay, then 1 hour is made up of 3,600 seconds. So 3,600, 60 minute times 60 second, because those two numbers you need to multiply, then you get 3,600 second. Okay, now let's see what units I can cancel out and double check my units. Hour cancels out with hour. So that's velocity, in this case is given in meter per second. And my value is, let's write down my value, 13.89 meter per second. Since we're dealing with 50 kilometer per hour, so it's a 50 point, that means there are only two significant figures. If we pay attention to that, we can round off to two significant figures, and we can write it down as 14 meter per second. Now we have everything in right units, mass in kilogram and velocity in meter per second. Let's plug in those numbers. So now we can write down lambda equals to h over mv. Now we're going to plug in numbers with right units. So 6.63 times 10 to the negative 34. Rather than writing down joule times second, I'm going to write down in terms of kilogram and meter square. So kilogram meter square per second. Make sure to double check, because it's joule times second. Joule is kilogram meter square per second square. Then you are multiplying by also by second. That's how we get kilogram meter square per second on the top. On the bottom, mass is in kilogram, so it'd be 85 kilogram times velocity is in 14 meter per second. Now that should, let me see whether I have my setup right after cancellation of units. Per second would cancel out. Kilogram would cancel out with kilogram. Now I have meter square on the top and meter on the bottom, so my final unit would be meter, and wavelength has to be length unit, so it must have the meter unit. I would like you to calculate this number and fill in that gap. Okay, now we're going to do problem number 43D, page 243. The question is, calculate the wavelength of an ozone molecule. Ozone is O3. Ozone molecule in the upper atmosphere moving at 550 meter per second. The velocity is given. The velocity is 550 meter per second. Again, this is a matter wave calculation, and don't forget that we need to have this expression, lambda equals to h over mv, and we already know h value is 6.63 times 10 to the negative 34 joule times second, and mass has to be in kilogram. Again, I'm reminding this, it has to be in kilogram, and velocity has to be in meter per second. Now velocity is already given in meter per second, and we don't have a mass at this point for ozone or O3. Now it'd be easy, you know that how do I get molar mass. So look at periodic table. Each oxygen is about 16. So 15.99 you can safely round off to 16. And we have 3 oxygen. So molar mass would be 48 gram. So let me write down molar mass is going to be 48 gram per mole. But we need to calculate the value for a single molecule. So molar mass has to be changed to the value for a single molecule. And each mole is really a big number, 6.022 times 10 to the power 23. Again, let's do the dimensional analysis and change gram per mole to kilogram per molecule. The first step would be fairly easy. You can see that 48, let's do this dimensional analysis here. 48 gram per mole times, I want kilogram. Remember, the mass unit has to be in kilogram. So I need to change it from gram to kilogram. Since gram is on the top, I must have gram at the bottom and kilogram on the top. Now 1000 gram makes 1 kilogram. So you should read like this. At the bottom, 1000 gram kilogram. So kilo means 1000. So always double check that way. Now I can now cancel out the units that I don't, let me see whether my setup is right. By canceling out, we can tell you. Gram would cancel out. That gives me kilogram on the top and mole on the bottom. Now I need to have a molecule. Okay, so I need to cancel out mole of ozone. So mole on the top. I forgot to write down ozone, but that's okay as long as we understand. So 1 mole of ozone means 6.022. It's also called Avogadro's number times 10 to the power 23 molecules. Don't get confused between mole and molecule. Molecule is nothing but label, kind of substance you are dealing with. And mole means a big number, like 6.022 times 10 to the power 23. So now I can cancel out mole on the top with mole on the bottom. Now I would have kilogram mass per molecule. And let me have that number. So that's going to give you, at least I got this number, 7.97 times 10 to the power minus 26 kilogram. Make sure you independently do this calculation. Now I have every quantity that I need to calculate wavelength. So next would be plug in your number in this expression, lambda equals to h over mv. So that's what you're going to do next. Lambda equals to h over mv, where h is 6.63 times 10 to the power minus 34 joule times second. So joule times second I can write down in terms of kilogram. So joule is kilogram meter square per second square times second would give me kilogram meter square per second. That's joule times second. And I must have at the bottom the kilogram is 7.97 times 10 to the negative 26 kilogram. Make sure you double check all these numbers and the units. That's mass. Now I need the velocity, which is already in right unit, 550 meter per second. Let's see whether my setup is right. By cancellation of the unit, I must get length unit because that's the unit of wavelength. So let me see what units I can cancel carefully. Kilogram cancels out with kilogram. Per second goes with per second. And you have meter square on the top and meter on the bottom. And that should give you meter as your final answer. And that's right. And it should be meter. So let's write down here our final answer here. And meter is the unit. Make sure you do this calculation and have your answer in this space given. And that way you'd learn how to calculate wavelength of different matter moving at different velocities.